Welcome back to The Explainer. Today, we're decoding an insidious form of electrical pollution that's hiding literally right inside our modern technology. We design everything around this perfect, smooth, sinusoidal power, but ironically, our own devices are degrading the grid with high-frequency anomalies. So let's dive right in and break down the science of harmonic distortion. You know, we usually treat grid electricity like it's this pure, endless flow of perfect energy. But the reality is quite a bit messier. Modern loads are constantly degrading power quality, pulling down system efficiency, and causing some serious premature equipment failures. And this invisible degradation, it is happening in the circuitry all around you right this very second, silently compounding inefficiencies across both massive commercial facilities and residential grids. Here is our quick roadmap for today. We're covering 1. The perfect wave distorted. 2. How harmonics are born. 3. The harmonic family tree. And finally, 4. Equipment under attack. All right, starting things off with Section 1, the perfect wave distorted. Okay, so what actually is a harmonic? Basically, it's a sinusoidal voltage or current component, but the absolute crucial part here is that its frequency is an exact integer multiple of your fundamental system frequency. We aren't just talking about random electrical noise. These are highly structured mathematical components perfectly locked in with the base frequency. So if your fundamental frequency is F1, your Hth harmonic is exactly H times that base. That perfect locked-in synchronization is exactly why they are so incredibly stubborn and hard to filter out of a complex network. For most of us, that fundamental frequency is typically going to be 50 or 60 hertz. Think of this pure sine wave like a single perfectly resonant note played on a finely tuned instrument. Our entire global electrical infrastructure, from those massive step-up transformers at the power plants all the way down to the low-voltage wiring inside your actual walls, was engineered specifically to carry this one pure note. All of our standard calculations for impedance, reactance, and load limits completely rely on this steady baseline. But then, thanks to Jean-Baptiste Joseph Fourier's brilliant mathematical principles, we know that any distorted periodic waveform is really just that perfect fundamental sine wave totally hijacked by higher frequency harmonics stacked right on top of it. When a third, fifth, or seventh harmonic superimposes over a standard 60 Hz wave, they just mathematically add together. The peaks and valleys literally collide. That smooth, beautiful curve warps into a jagged, non-sinusoidal reality that our devices are just forced to swallow. And this severely alters the peak voltage and RMS values, completely changing how power is delivered to sensitive electronics. Moving right along to Section 2, how harmonics are born. So where are these mathematical gremlins actually coming from? Well, the main culprits fracturing the perfect wave are nonlinear loads. A linear load, like an ideal resistor or a standard induction motor running at steady state, is pretty predictable. Feed it a smooth voltage, and it draws a continuous proportional current. Nonlinear loads, on the other hand, are chaotic. Even if you supply them with an absolutely pure voltage source, their impedance changes drastically during the electrical cycle. And that varying impedance causes them to draw current in these irregular, abrupt pulses, which essentially injects harmonic currents right back into the power system. Now, here is the ultimate irony. The very technologies driving our green, energy-efficient modern world, they are actually the greatest sources of this distortion. Power electronics that rely on the rapid switching of IGBTs, thyristors, and MOSFETs inherently create harmonics. Why? Because they literally chop up and interrupt the current flow thousands of times a second to modulate power. Whether we're talking about an EV traction inverter, a variable frequency drive, or even standard fluorescent lighting ballasts, that switching action just hacks away at the waveform. Add in the magnetic saturation from transformers running hot, or the completely chaotic arcing of industrial electric arc furnaces, and you start to see that our energy efficiency often comes at a massive cost to our power quality. Let's classify these things in Section 3, the harmonic family tree. It's important to realize that not all harmonics behave the same way in a system. Even harmonics, like the second, fourth, or sixth multiples, are actually pretty rare under normal conditions. If you see them, they usually point to a temporary DC offset, some half-wave rectification, or a severe system fault, and they usually vanish quickly once the system stabilizes. The real, persistent threat, that comes from the odd harmonics, the third, fifth, seventh, and 11th. They create symmetrical waveform distortion and act as the long-term steady-state residents of our power grid, generated continuously by all those everyday nonlinear loads we just talked about.
If we look at these odd harmonics by their phase sequences, we can see exactly how they physically attack our systems. Positive sequence harmonics, like the 7th, create a magnetic field that actually rotates in the same forward direction as the fundamental power. But negative sequences, most notably the 5th and 11th, do the exact opposite. They generate a magnetic field that rotates in reverse, literally fighting the forward momentum of rotating machinery. And then, most terrifyingly, we have these zero-sequence harmonics, often called triplens, which include the 3rd and 9th. In a perfect three-phase system, currents are supposed to cancel out at the neutral point. But because triplens are perfectly in phase with each other across all three legs, they don't cancel. No, they mathematically compound.
Which perfectly sets up our final section, equipment under attack. These high-frequency currents are absolutely ruthless to our physical infrastructure. Take capacitor banks, for example. Because capacitive reactance naturally drops as frequency goes up, these banks accidentally act as low impedance sinks. They basically invite all these high-frequency harmonics inside, causing massive overcurrents and risking severe dielectric breakdown or a highly destructive resonance. At the same time, transformers are out there suffering extreme internal heating from high-frequency eddy currents and hysteresis losses in their iron cores. They require massive derating or super specialized K-rated designs just to survive the heat. On top of that, microprocessor relays, which rely on precise voltage zero crossings, get completely confused, miscalculate line impedances, and trigger false trips that totally blind our protection systems. And this leads to a total snowball effect, a true escalation of damage across the grid. Just imagine the mechanical toll on an industrial scale. A fifth harmonic creates reverse torque. That means a massive induction motor is actively being violently pushed backward while the fundamental power is trying to push it forward. It literally shakes the machine apart, inducing severe torsional oscillation and chewing through bearings. And remember those triplen zero-sequence harmonics because they sum together instead of canceling? The neutral wire, which normally doesn't even have a circuit breaker because it shouldn't carry heavy loads, gets slammed with current overloads that can easily exceed the main phase currents. It creates a massive, totally hidden fire hazard right inside common three-phase commercial systems. So, as we wrap up this explainer, I want to leave you with a thought. Just how heavily distorted is the power flowing into the very screen you're using to watch this right now? With every single new inverter, smart device, and rapid charger we plug in, we are fundamentally altering the power of our infrastructure. Understanding harmonic distortion isn't just theory. It's absolutely crucial for protecting the longevity, safety, and efficiency of our electrified world. Keep questioning what powers your life, and we'll see you in the next one.